Okay, everyone, here we go. This is for real this time, finally. Up here. Let's see what, who did this first of all? This is Adam. And while I'm doing that, who did this one? Thank you, Chelsea. And Rachel. And
Ashley.
Okay. So looking at what Adam did up here, he ended up with this x squared. Where'd that come from? Well, that was the product of the x and the x. I'm going to call that f, standing for the first terms. It was the first term out of these two and the first term out of these two. And then he did 7x, that's the outside two terms. And then he did 3 times x, that's the inside two terms. Then he did 3 times 7, that's the last term. So he kind of followed this, this algorithm that we talked about yesterday, FOIL. And he showed the kind of components in that order, and then he combined these like terms, the 7x and the 3x, to get 10. We still have a question, like why does that work? Why does what he's doing here as his first step, why is that allowed? But assuming it's allowed, does everyone see where those terms are coming from? Okay. And then going down here, Chelsea, she did same thing, the first two terms, x and x, that's first term. The outer terms, negative 6x, the inner terms, negative x, and the last terms, negative 1 times negative 6, getting positive 6. She followed the same algorithm to get the same terms. Rachel did the same thing here. 2x times 3x is 6x squared. Those are the first terms. Then the outer terms she did 2x times negative 2x. The inner terms 4 times 3x to get 12x. And the last terms 4 times negative 2 to get negative 8. And then combine like terms, negative 4x plus 12x. And Chelsea also, forgot to mention, combine her like terms, negative 6x minus x is negative 7x. And then Ashley captured this idea in general. The first terms times the first term out of A and B. The first term is A. Out of C and B, the first term is C. AC. And the outer terms, the ones on the outside of the multiply, A and B. And the inner terms, the ones on the inside of the multiply, B and C. And the last terms, B and B. In my first period class, us did this first problem like this, slightly differently. Took the first terms, x and x got x squared, and then next did the inner terms, 3x. And then did the last terms. Actually, no, did the outside terms next, plus 7x. And then did the last terms, 21. Is this equivalent to this? Why is this equivalent to this? Can anybody think of what property tells me that that and that are equivalent to each other? Yeah. So the distributive property is going to tell us something really important. You mentioned a name. Let's write that down. But it won't tell me, like, what tells me that I can take the 3x and the 7x and write it like that, or I could take it and write it like that, 7x and 3x. That's another question. But let's write the distributive property down. So we've got some properties. And this is kind of like our tool case, or our, what do you call that? toolbox, our toolbox. The distributive property says that when you have A multiplied by B plus C, that's the same as what? AB plus AC. Okay. Now, is there a deity that comes down and says that when you're playing with numbers, that you have to have your numbers follow the distributive property? Is there like a structure that says you must use numbers that follow the distributive property? There isn't really. There's nothing that tells you that you have to allow the distributive property to be true. It's really a choice that we make. And it's an interesting choice, and I think it's a good choice, and it's a choice that we're going to make in the class, and that many mathematicians before us have made. If we don't allow the distributive property, we end up with things that behave in very different ways. So we're going to say that this is true, but we're not going to prove that this is true. I'm not going to prove to you that the distributive property is true. Why? Because I can't. We have to have somewhere to start. The way that we'll make proofs, and we'll see in just a moment, is we'll use these things to prove other things. And then the natural question is, well, how do you know these are true? We don't know they're true. We're pretending they're true. That's math for you. Right? I made this analogy before where we had the picture of the cloud. Did I draw the cloud before? And we built on top of the cloud a tower of a bunch of proofs. Right? The cloud is the axioms. That's the things we assume are true. Right? These properties are axioms. We assume are true. Assume. It means we kind of like we pretend. We play the pretend game. Like, you know, when you were a little kid, you probably played pretend games. Most young children do play pretend games where you're like, pretend that I'm an astronaut, right? And then I'm walking on another planet where there's no gravity, or where there's really low gravity, and I could jump really high. And if you're playing that game and someone says to you, wait, you didn't actually jump high, you only jumped like a little bit off the ground, right? That's kind of not playing the game. You're like stepping outside the game. And if you were a little kid, you'd say, no, we're playing pretend. You might not even say that. You might just get frustrated because you're playing pretend. And everybody knows that when you're playing pretend, you just kind of play along. The same thing is true in math. All of math is kind of that pretend game where you've got some stuff that you just like say, let's pretend this is true. Don't question it. Let's just pretend this is true. Okay. Are there any other things that we pretend? And is there one, does anybody notice, looking at this, comparing that 3x plus 7x to the 7x plus 3x, is there anything that tells me I can take my addition and I could do it like, I can add 3 to 2, 3 plus 2, and then I'm going to get the same thing as if I do 2 plus 3? What tells me I can change the order when I'm adding things? Sam? Yeah. Can anybody finish that word for him? Commutative. Commutative property. And he's saying that we're going to allow the commutative property of addition. And that the commutative property of addition says that you can do a plus b and get the same thing as if you do b plus a. Right? That we can do 3x plus 7x and we get the same thing as if we do 7x plus 3x. So how do we know these two are equivalent? The reason we know they're equivalent is because of the commutative property of addition. That's what tells us. Are there any other commutative properties? Subtraction, let's try subtraction. Is A minus B the same as B minus A? It doesn't work. Remember, these are things we assume. Let's say we assume this is true. Play along, come on everyone. We're on the playground here. Play along. What kind of numbers do we have? What's true about our numbers if this is true? We only end up with one number. What number do we end up with? 0. If there's only one number, and 0 is the only number, right? Or you can really make it any number, but if there's only one number, we restrict ourselves to one number, then we know A and B are going to be the same thing. And we subtract 0 minus 0, 0. That's the same as 0 minus 0. Right? Kind of annoying. We want to have more numbers than 0. Like, imagine counting if the only number you have is 0. 0, 0, 0. Like, you can't really do some of the stuff that we want to do. But you can play that game, and it might be an interesting game to play. Okay, but we choose not to have the commutative property of addition. What about division? A divided by B. Is that the same as B divided by A? What kind of number would I have if I allowed that? What number, if I had just one number, what number could I plug in there? And then I would end up with a different number as a result of doing the division, yeah. What's that? What happens if you do 0 divided by 0? You don't actually get 0. You can't, we make it as one of our rules that you can't divide by 0. Now, maybe you could allow that you're going to divide by 0. Good argument. But I think 1 is probably a more natural one that might resonate more with you. Like 1 divided by 1, what is that? 1. And we haven't ended up with a new number. It is kind of matches up with the other axioms that we have. So if we wanted to have the commutative property of division, then we'd have to only have the number 1. But we want to have A, B, and C as real numbers. We want any real number. So we're not gonna do division. What about multiplication? What does that look like? A times B equals B times A. And does that work? Does that match our intuition, what we've been doing, what you've learned so far with multiplication? There's one more. No time for it. We'll have to do it tomorrow. That makes me sad. But we'll have to start with the one remaining property, and then we'll do a proof. See you all tomorrow.